In this lesson, we will examine the pressurization control systems fitted to modern airliners. We will look at the necessary safety devices fitted and the indicating systems available to the crew. Modern aircraft operate more efficiently at high altitudes, and they have high rates of climb and descent. In order to take advantage of these properties, the interior of an aircraft flying at high altitude is pressurized to allow passengers and crew to function normally without the need for additional oxygen. Up to an altitude of 10,000 feet, the air pressure, and consequently the amount of oxygen, is sufficient for humans to operate without too many problems. However, the effects of lack of oxygen can become apparent at altitudes above this. To prevent any risk of problems due to a lack of oxygen, it is a regulatory requirement that cabin pressurization systems are designed to produce conditions equivalent to a maximum of 8,000 feet in the aircraft cabin. This means that there is no need for oxygen equipment except for emergency use by crew or passengers. The difference in pressure between the pressurized hull and the atmosphere produces stresses, which are applied cyclically every time the aircraft is pressurized and depressurized, causing fatigue, which can ultimately lead to structural failure. The airframe structure must be strong enough to withstand the differential pressures generated. The aircraft manufacturer will set as a structural limit a maximum differential pressure. That is, the difference between the pressure inside the pressurized compartment and the pressure of outside air, which the pressurized hull can safely withstand. The normal operating maximum will be slightly lower than this. On modern transport aircraft, the normal operating maximum differential pressure is typically between 8 and 9 pounds per square inch, or psi, or between 552 and 621 hectopascals. This maximum differential pressure, along with the maximum permitted cabin altitude of 8,000 feet, will set a maximum for the altitude at which the aircraft can operate. As you can see from this barometric pressure table, the air pressure at 8,000 feet is 10.91 psi. So if the manufacturer has set the aircraft's maximum differential pressure at 8.2 psi, then the minimum outside pressure is 10.91 minus 8.2, which equals 2.71. We can see from the chart that this equates to just a touch over 40,000 feet. Thus, an aircraft with a maximum differential pressure limit of 8.2 psi will have a maximum operating altitude of 40,000 feet. This is, of course, the pressurization limit. The aircraft's maximum altitude may be further limited by other factors. If the maximum permitted differential pressure is reduced by an aircraft defect, for instance a cracked cockpit window, the maximum aircraft altitude will also be reduced by the need to maintain the maximum cabin altitude at 8,000 feet. For instance, if the maximum differential pressure is reduced to 6 psi, then the minimum outside pressure will now be the pressure at 8,000 feet, which is 10.91 psi minus 6, which equals 4.91 psi. From the table, the altitude equal to 4.91 psi is approximately 27,000 feet. This is the maximum altitude limit with a differential pressure of 6 psi. The passenger cabin, flight deck, and cargo compartments are normally pressurized. The landing gear bays, radome, and the tail and nose cones are unpressurized. Cabin pressurization is achieved and controlled by having a constant mass flow of air entering the cabin from the conditioning system, and then varying the rate at which it is discharged to atmosphere. The constant mass flow of air is supplied by the air conditioning packs via their mass flow controllers, and is discharged to atmosphere through the discharge or outflow valve or valves. The position of the outflow valve can be controlled either automatically by an automatic pressurization controller or manually by the flight crew. Closing the outflow valve reduces the outflow and increases the cabin pressure, causing the cabin altitude to descend. Opening the valve has the opposite effect, increasing the outflow, reducing the cabin pressure, and causing the cabin to climb. There are a number of safety devices which must be fitted to any cabin pressurization system. The safety valve is a simple mechanical outwards pressure relief valve, fitted to relieve positive pressure in the cabin when the normal maximum pressure differential allowed for the aircraft type is exceeded, preventing the structural limit from being exceeded. This valve is totally independent of all other control systems, and will open if the cabin differential pressure rises to approximately 0.25 psi above the normal maximum. The regulations stipulate that there must be 2 safety valves fitted. The fuselage is designed to withstand the positive differential pressure produced by the pressurization system. However, it is not able to withstand the crushing forces that a negative pressure differential would produce. To prevent this problem, simple mechanical inwards relief valves are fitted. They will open if the pressure outside the aircraft exceeds that inside by 0.5 to 1.0 psi. There must also be 2 of these valves. The inwards and outwards safety valves may be combined together in one unit, or may be completely separate components. They are positioned above the aircraft flotation line, so that in the event of a landing on water, they will not allow the water to flow into the aircraft. The dump valve is a manually operated component. It enables the crew to reduce the cabin pressure to 0 for emergency depressurization. This valve may, in some systems, also be used as the air outlet during manual operation of the pressurization system. Blowout panels are fitted in the floor between passenger and cargo compartments, in order to prevent excessive differences in pressure occurring between these areas in the event of, for example, a cargo door opening in flight. The panels are normally fitted under passenger seats, and they are held in place by springs. If a cargo door should open, then the pressure differential between the passenger and cargo compartments will overcome the springs and the panels will open, equalizing the pressure between the compartments before the floor structure is damaged. Some systems are fitted with a ditching control, which will close all the discharge valves in the event of a forced landing on water. This will reduce the flow of water into the cabin. There will be an oral or visual warning if the cabin altitude exceeds 10,000 feet. The oral warning may take the form of a horn, and the visual warning a red light in prominent view of the pilot. There is normally a horn cutout button which can be depressed to cancel the horn. That is the end of the lesson. You should now know that the maximum permitted cabin altitude is 8,000 feet, and that the normal maximum positive differential pressure is between 8 and 9 psi. You should understand that the aircraft's maximum operating altitude is dependent upon the maximum differential pressure, and given a barometric pressure table, you should be able to calculate this maximum altitude. You should also know that the pressurization is controlled by having a constant mass flow of air into the fuselage and controlling its exit using outflow valves. You should understand the purpose of the various safety devices fitted to a pressurization system. The positive outward opening pressure relief valves prevent the structurally limiting maximum differential pressure from being exceeded, and negative inward opening relief valves prevent the pressure inside the cabin becoming less than that outside. The dump valve is used to completely depressurize the aircraft, and the ditching control is used to close all outflow valves prior to the aircraft landing on water. Blowout panels are fitted in the floor between passenger and cargo compartments in order to prevent excessive differences in pressure occurring between these areas. And finally, an oral or visual warning will be given to the crew when the cabin altitude exceeds 10,000 feet.